Hello, I'm Dr. Samidhi Navaratna from the Department of Community Medicine. This lecture is on correlation and regression. It's an entirely different topic to chi-square test that we discussed last week. Therefore, I won't be reiterating any points from the last lecture. Straight away, let's start the lecture proper. Learning outcomes. By the end of this lecture, each of you should be able to give examples of research questions that would be appropriately answered through correlation or regression analysis. Secondly, you should be able to interpret scatter plots describing association between variables. Third one is interpret results of correlation and regression analysis presented in tables and figures from the public health literature. Then finally, describe the linear regression model and interpret the slope and R-square. So let's start with the first subtopic of this lecture, correlation. So in general terms, correlation means an association. Similarly, in terms of statistics, a correlation means a relationship between two continuous variables. Introduction to correlation. Correlation is a statistical method used to determine the existence of a relationship between two continuous variables. So there are several types of correlation coefficients. The one that would be explained in this section is called the Pearson's correlation coefficient and is named after Carl Pearson, who is the statistician who pioneered the research in this area. So Pearson's correlation coefficient measures the degree of association and is denoted by simple r or capital R. And this correlation coefficient can range from a minimum value of -1 to a maximum value of +1. Correlation coefficient R explains the strength as well as the direction of the relationship between the two continuous variables under consideration. Therefore, a correlation coefficient of +1 indicates a perfect positive relationship, whereas a correlation coefficient of -1 indicates that there is a perfect negative relationship. On the other hand, a correlation coefficient of 0 means that there's no linear relationship between the two variables. The second thing you need to keep in mind is high correlation may indicate a strong association but not causation, because sometimes you need to take the complexity of interrelationships into account, particularly when interpreting the results. For an example, a researcher may find a statistically significant relationship between the IQ level of a medical student and the final MBBS results. However, as we know, there are many other variables such as hours and quality of studying, motivation, influence of parents, then physical facilities, etc. that affect the outcome variable. Then, in addition, there are sometimes a third factor that can be associated with both the predictor variable as well as the outcome variable, and therefore it looks like there's an association, but it's a spurious association. For an example, now sometimes back in Europe, in a study, they found that the number of cups of coffee taken per day was associated with the number of deaths due to myocardial infarction. But later on they found that it's because the third factor, that is the cold weather, affects both the consumption of coffee as well as more heart disease. So you have to be extra careful when interpreting results. The third one is value of the R doesn't change according to which variable is labeled as X and which variable is labeled as Y in a scatter plot. So this is regarding correlation, but with regard to regression, you need to be careful when you label the variables as independent and dependent. Then finally, value of R is independent of the unit of measurements of the two variables under consideration. Moving on to the scatter plot. The scatter plot helps to determine the nature of the relationship between two continuous variables. The initial judgment of a relationship between two continuous variables must always be sought using a scatter plot before you construct the correlation coefficient or the regression line for those two variables. So let's draw a scatter plot for this set of data, the weight and the height. Now we have already discussed in the introduction that the value of the R doesn't change according to which variable is labeled as X and which variable is labeled as Y in a scatter diagram. Therefore, let's draw a scatter plot for this set of data using weight as the x-axis and height as the y-axis. Okay, so let's see. So this is the scatter plot, and as you can see, there's a linear-like relationship between the height and the weight as shown by this trend line. And the R squared here is given as 0.6125, and you can get the correlation coefficient R by taking the square root of this, and it comes as 0.78, right? And now let's see whether by changing the axis, that is by taking height for the x-axis and weight for the y-axis, whether this correlation coefficient would change. And you know, usually when you draw a chart, you take the independent variable to the x-axis and the dependent variable to the y-axis. And in this case, you know that weight is dependent on height and not vice versa. So the correct way of drawing it anyway, the logical way of drawing it anyway would be by taking the height into the x-axis and weight to the y-axis. So let's see. So this is the second scatter plot, and we have taken the height to the x-axis and the weight to the y-axis. We have changed them, and as you can see, yet again we have got a linear relationship, and the R square remains the same. So therefore, which means by we can confirm the fact that the value of the R, the correlation coefficient, doesn't change according to which variable is labeled as X and which variable is labeled as Y in a scatter plot. However, this is not the case with regression. You have to be particular about taking the independent variable to the x-axis and the dependent variable to the y-axis with regard to the regression line, because otherwise you can't interpret it. A little bit more about the scatter plots, the positive and negative correlation. As you can see in this scatter plot, there's a positive relationship between the two variables, the number of TV watching hours and the weight gain. And as you can see, in a positive correlation, large values of X are associated with large values of Y, and small values of X are associated with small values of Y. And in contrast, in a negative correlation, there's an inverse relationship. That is, the large values of X are associated with small values of Y. Right? Large values of X are associated with small values of Y, and vice versa. That is, the small values of X are associated with large values of Y. Scatter plot and correlation coefficient values. As we discussed in the introduction, correlation coefficient value of +1 indicates a perfect positive correlation, and a correlation coefficient value of -1 indicates a perfect negative correlation, and everything other values falls in between. And correlation coefficient equals to 0 indicates that there's no linear correlation whatsoever between the two variables concerned. Formula for the correlation coefficient is calculated by using this common equation. The correlation coefficient equals to the covariance of X and Y divided by the square root of the product of variance X and variance Y. So it is written in this way, and these are the equations taken for each of this numerator and the denominators, and then when these are substituted to the equation, you get this. It's the, you know how you find the variance by the least square method, and when you simplify this, the ultimate equation that you get is this. So by using this, let's see whether we can construct the correlation coefficient for a given example. A radiologist wishes to see whether an association exists between the extent of the myocardial infarction and the ejection fraction. Find the strength of the association using the following data. So this is the set of data, and in the first column they are given the volume of the myocardial infarction in milliliters, and in the second column the ejection fraction as a percentage. So to draw the scatter plot, we have to decide which variable we will put to the x-axis and which variable we will use for the y-axis. So as you know, in a correlation coefficient calculation, it doesn't really matter. But however, since we'll be using the same example for the regression equation calculations and the regression line determination, so we'll use it in the correct way. We'll use the independent variable to the x-axis and the dependent variable to the y-axis. So in this case, the independent variable is the volume of the myocardial infarction, and the dependent variable is the ejection fraction. So here it is. We have taken the ejection fraction, the dependent variable, to the y-axis, okay, and the volume of myocardial infarction to the x-axis. So let's see. So this is the scatter plot, and as you can see, there's an inverse relationship or a negative correlation between the two variables. And now we have to calculate the correlation coefficient and see whether the correlation coefficient be a negative one. We'll see, right? So this is the equation we have learned, and we need some information for that. We need the sum of the product of x and y variables. Then we need the sum of the x variable, sum of the y variable, and we need the sum of the x squared, and then square of the sum of x, then sum of the y squared, and square of the sum of y. So let's do it step by step. We'll find this information, and to do that, let's expand this table. First, let's find the x squared. So here I have squared each of these values and put it in this middle column. So next, let's find the y squared. So it's in this third column. Then fourth step would be to find the product of x and y. And the final step is to sum all these up. So we have the sum of x here, sum of x squared, sum of the product of x and y, sum of the y squared, and sum of y. So we have all the information we need to calculate the correlation coefficient. So let's substitute these values to this equation. So the calculated R value is minus 0.93. So which means there's a good negative correlation between the two variables. The interpretation, the R value indicates a very strong negative association between the extent of the myocardial infarction and the ejection fraction. Other formulae used to calculate correlation coefficient. So certain books describe slightly different variations of the same equation to calculate the correlation coefficient. So for your information, I just listed two here. The significance test for correlation coefficient is actually a t-test, and this is the equation. The degrees of freedom is calculated by n minus 2. So the steps you need to follow in the hypothesis testing is the same as those you learned for the other hypothesis testing tests in the previous lectures. However, you need not by heart this equation, as you won't be questioned on this, and we don't expect you to carry out calculations using this equation either. So the key thing to remember is that the t statistic for the correlation depends on the magnitude of the correlation coefficient, that is the value of the R, and the sample size. Therefore, with a large sample, even weak correlations can become statistically significant. So that's the worry. So as I mentioned, we won't be asking you to do hand calculations for this significance test. And anyway, you need to know the symbol for the population correlation coefficient, that is rho. And the null hypothesis for a significance test for correlation coefficient is that there's no correlation, right? So, which means that rho equals to 0. Moving on to the coefficient of determination symbolized by r square. Sometimes it's referred to as goodness of fit, right? In univariable linear regression, it's just the square of the Pearson correlation coefficient, R, right? So, it's easy to calculate if you know the Pearson correlation coefficient. And vice versa, if you know this value, it's easy to derive the correlation coefficient. You just need to take the square root then. It's a complex value used to determine how much variability of one factor can be caused by its relationship to another factor. It represents a value between 0 and 1. As you can see, there's no negative value because when you square it, the value becomes positive anyway. It's used for trend analysis. Moving on to our next subtopic, regression. As we discussed in correlation, in studying the relationship between two variables, a researcher first constructs a scatter diagram through which the nature of the association is determined. Since we are only interested in the linear nature of the association for the purpose of this lecture, we determine whether the association is a positive linear association or a negative linear association. Then the second step was to calculate the correlation coefficient. And the importance of that is to determine the strength of the association. And then we also learned that we need to look whether that association is statistically significant. Having done all that, the last step is to determine the regression equation, which draws the regression line that fits best to the data given. Univariable or simple linear regression introduction. The correlation coefficient, as we discussed, indicates how closely these observations conform to a linear equation. Regression models go a step further and can be used to predict the value of one variable given the other. The assumptions for valid predictions in regression include: first one, for any given value of the independent variable, the value of the dependent variable must be normally distributed. Second one, the standard deviation of each dependent variable must be the same for each value of independent variable. Then finally, the observations must be independent. Continuing with the introduction to univariable linear regression, apart from the requirements we discussed in the previous slide, the relationship between the two continuous variables need to be linear. We can find this out through a scatter plot. And then in general, only the values within the range of observations of the independent variable should be used in prediction. This we would discuss further with an example later on in this lecture. Then thirdly, regression determines the equation of the regression line, which is the line of best fit for the given data. Then again, regression is a statistical technique that allows you to investigate the relationship between a dependent variable and one or more independent variables. So if there is one independent variable, then the model is known as simple linear regression or a univariable linear regression or a univariate linear regression. If there is more than one independent variable, then the model is known as multiple linear regression or multivariate linear regression or multivariable linear regression. Simple linear regression model is derived by the algebra equation for a straight line y equals mx plus c. So it derives the best fitting line for a given data set. Best fit means that the sum of the squares of the vertical distances from each point to the line are at a minimum. So let's look at the equation. For a population, the equation is y equals beta naught plus beta 1 x plus eta, and here eta represents an error term. Therefore, the functional equation is y equals beta naught plus beta 1 x, and for a sample we use the hat sign like this, and certain books might use B instead of beta, and some books and some journals use alpha in place of beta naught. And as we discussed, beta naught is the intercept, and intercept is the point at which the line crosses the y-axis, and then beta 1 is the slope. So look at this scatter plot. As you can see, beta 1 is calculated by dividing delta y by delta x. So delta y divided by delta x can be interpreted as meaning a quotient of small differences in y and x, right? So it is, this notation delta is usually used in calculus, especially in physics, to mean tiny changes or very small increments. Therefore, these tiny changes actually allow us to find the derivative, which is the slope at a point. So there are several equations that can be used to derive the regression line by estimating the intercept and the slope for a given data set, and these are just two of those equations. So to calculate the constant, you can use this equation, and to calculate the regression coefficient or the slope, you can use the second equation. And as you can see, these formulas use the same values we use to calculate the correlation coefficient. So it's easy. So that is why I prefer these two equations. Example for the simple linear regression. It's the same example we used to calculate the correlation coefficient. A radiologist wishes to see whether an association exists between the extent of the myocardial infarction and the ejection fraction. Find the equation of the linear regression line and interpret the result. Predict the ejection fraction expected for a myocardial infarct of 1.7 milliliters. The calculated R square, that is the coefficient of determination, is 0.8665. Interpret the result. So the first step is to look at the data and derive the necessary information. And since we derived everything in the first example, we'll put it here. So we have all the necessary information to calculate the beta naught and beta 1. So this is the scatter plot we initially derived, and as you can see, there's an inverse relationship or a negative correlation between these two variables. So let's substitute these values to these two equations to find beta naught and beta 1. So the value for beta naught or the intercept or the constant for the equation is 77.58. And let's see what would be the beta 1, that is the value for the slope. The value for the regression coefficient or the beta 1 or the slope is minus 11.54. So the equation would be, this is the general equation. The equation for this example is y equals 77.58 minus 11.54x. So next we have to interpret it. Interpretation is, for each 1 milliliter increment of the myocardial infarct, the ejection fraction will reduce by 11.54%. So the next question is to predict the ejection fraction expected for a myocardial infarct of 1.7 milliliters. So to do that, you just need to substitute a 1.7 for this equation. So in the place of x, we put 1.7. So the answer is 57.962%. The third question is, the calculated R square is 0.8665. Interpret the result. Interpretation is, of the observed values, 86.65% of the data points will fall on the regression line, making it a very good fit. So let's look at the scatter plot. This is the regression equation. And this is R squared. So I have extended the line to show the intercept here. So it's 77.578. Another example to understand the concept of simple linear regression. Using the data set, derive the regression equation. Interpret the regression coefficient and coefficient of determination. So this data set you have seen before. We used it to draw the scatter diagram. And since this is a regression example, we need to determine the independent variable and the dependent variable correctly and place the independent variable in the x-axis and the dependent variable in the y-axis. So in the previous example, when we used this data set, we determined that height is the independent variable and weight is the dependent variable. So I have labeled these two data sets like that. So let's draw the scatter plot, and as you can see, there's a positive correlation. And I'm not going to derive this equation, the regression equation, manually, but you can practice derivation of this equation using this data set, just like the previous example. Now we need to interpret the results. According to this model, for each additional centimeter of height, the weight of a person increased by 0.8744. According to the coefficient of determination, 65.93% of the data points would fall within the regression line. So if we extend the this regression line, you can see that it goes towards the negative side. So this just I wanted to prove that in general only the values within the range of observations of the independent variable should be used in prediction. Because now if you can understand, now at this point this is the height is maybe 75, but weight is 0. So does such a person exist? The weight of that person is 0, so it doesn't make any sense at all. And at some point the weight even becomes minus. So you can't use the regression line for prediction outside the range of values of the observed range of values. So that is the point I wanted to make to you at this point. More advanced methods of regression include multiple linear regression model, logistic regression model, Cox regression model, and Poisson regression model. Now we have come to the end of this lecture. If we just recap what we learned in this lecture. In the initial part of the lecture, we learned about the scatter plots and about the Pearson's correlation coefficient denoted by R. Then we just touched upon the significance test for correlation coefficient. Then we learned a little bit about the coefficient of determination, which is denoted by R square. Then finally, in the latter part of the lecture, we discussed the basics of regression. Particularly, we learned about the simple linear regression model. Now, mind you, what I want to tell you here as the final message is that whatever you learned in this lecture, the calculations and whatever the test, and whatever you learned in the previous lectures, particularly the inferential statistics lecture series and the categorical data analysis lecture, the chi-square test, well, all those calculations actually you don't have to do manually, particularly when you are engaged in research in future, because you have many statistical software that can do the job for you quite efficiently and easily, right? But for the exam purposes, you may have to do certain small calculations. However, the objective of this whole biostatistics module is that you will learn the applications. You need to have a basic background knowledge to know what to do with the statistical software. So, for that, you need to have a proper knowledge of the tests, the applications, and how to interpret the results you get. Right? So, those are the important things that you need to keep in mind. And having said all that, I think now I can wind up the session. And one thing, please do the quiz, and I will upload the answers for the third quiz along with this lecture. And if you have time, please consider filling up the feedback form. Thank you.